Hi everyone, I'm Yang. I'm a new assistant professor at the NUS. Uh, I just got my PhD in computer science from UC Berkeley this summer. So this talk, I'm going to introduce how can we speed up the training of deep neural networks. For example, how can we train BERT in 76 minutes? So let's go to my talk. In the last 3 years, actually, supercomputers are becoming popular to the leading AI companies. For example, Microsoft put some supercomputer to the cloud. Google now has its own supercomputers, TPU pod. Facebook made a submission to the top 500 supercomputer list. Amazon had HPC Cloud, which is for the supercomputing applications. So here is a quote from Andrew Ng, who is a deep learning researcher. From this quote, we can say we can see that maybe in the future, deep learning and AI will need more and more supercomputer and high performance computing. So why they like supercomputers? I mean, why the leading AI company like supercomputers? Because the computation of deep learning is very expensive. For example, if we want to use ImageNet to train rest ability model, we need to finish 19 epochs, and for each epoch, we need to process 1.3 million images. For each image, we need to finish 7 points of billion operations. So in total, it's 10 to the power of 18 operations. So if we only use one CPU, it's going to take us several months, it's like forever. If we use one M40 GPU, it will take us 14 days. So even we have 8 P100 GPUs, it still can take us 29 hours. So however, in 2017, we know that supercomputers can process 2 times 10 to the power of 17 operations per second. So the question is, if we use supercomputer for this ImageNet resonance ability training, can we finish it in 5 seconds? Actually, the answer is no, because we cannot make a full use of a supercomputer because we need to parallelize deep learning over sound processors. There are several different approaches like model parallelism or communication optimization or data parallelism. So for this talk, I'm going to introduce data parallelism. For data parallelism, the idea is large base training. We want to increase the base size to very large. In this way, we can process more samples, like more images per iteration. However, when we increase the base size to very large, we will lose accuracy. Here, let me give you a figure. The horizontal axis is epochs. The vertical axis is accuracy. The blue line is the baseline. The black line is a live-by training. Clearly, you can see by training the same number of epochs, live-by training is going to lose accuracy, because as this paper shown in 2017, live-by training is a sharp minimum problem. So there is a generalization gap between training and testing. So even we can train a good model, it's very hard to generalize. So we want to solve this problem, and we studied a long time and did some numerical experiments, and we found something interesting. I think we found a pattern. So we found when increase the base size to very large, the ratio between the normal width and normal gradients is very interesting. So let me visualize this ratio. The horizontal axis is different layer, vertical axis is this ratio. So the application is image data training with LXNet. Clearly, you see for layer 6, its ratio is very high, but for layer 1, its ratio is low. So that means for live-based training, we cannot use the same learning rate for all the layers. We know in 2017, all the application, almost all the applications, they use the same link rate for all the layers. That's okay for small batch training, but for large batch training, you see if we use the toy example, we use the same link rate for layer 6 and layer 1. Layer 6 is okay, but layer 1 will diverge. So based on this important information, so we propose the idea of trust ratio. By using trust ratio, we can get a new algorithm, actually new optimizer, LARS, layer-wise adaptive rate scaling. Here, let me just briefly go over this algorithm to show you the key idea. So we first compute the gradients within each layer at the iteration t, and we initialize the trust ratio. And then we compute the norm of the gradients, and then we compute a second part ratio by layer-wise with the decay. Then we get the trust ratio. So you see, it's roughly the ratio here, right? So the normal weights and the normal gradients, but we add more terms here to make it more stable. And then we use the trust. Then we use the trust ratio to update the momentum, and then we update the weights. So the idea here is each layer can get its unique link rate. And also because the trust ratio is changing between different iteration, right? So here it's actually changing between different iteration. So this can give you adaptive scaling at the runtime. So I want to check our paper. But we can make this algorithm even better. So we know in the last 5 years, Atom optimizer is very popular. So the key idea of Atom is the first moment and second moment computation. So we want to put the trust ratio technique together with the first moment and second moment technique to build a new optimizer. So here, let me briefly introduce the second optimizer, LAMP, layer-wise adaptive momentum for batch training. So within each layer and at each iteration T, we compute the gradients. We compute the first moment, we compute the second moment, and then we do bias correction for first moment, do bias correction for second moment, and then we initialize the trust ratio. We compute the norm of the gradients, and we compute a second part of trust ratio by element-wise with the decay. And then we use trust ratio to update the weights. So idea here is we can have adaptive element-wise updating because for this kind of computation at element-wise or feature-wise. And also we have layer-wise correction because we use layer-wise trust ratio, and also element-wise with the decay here. Element-wise with the decay is more accurate. This is very important for the model like BERT, which has billions of parameters. So I propose the two algorithm LARS and LAMP. So I also want to implement why LARS and LAMP work. I want to implement why LARS and LAMP can solve the sharp minima problem. So why they can speed up training and why they can converge faster than IgG. So let me first introduce the dynamic of LARS. So here the horizontal axis is number of epochs, vertical axis is link rate. Clearly you can see so base size 256, base size 1K, base size 8K. You see I use AlexNet ImageNet training with LARS. Here layer 1, sorry. Here is layer 1, here convolutional part, here layer 1 bias part, here layer 5, and with part and convolution part. So we can see for a different base size, you see link rate is very different, right? So also for a different epoch, link rate is very different. And even within the same layer, layer 1 is the convolutional part and the bias part, the weighted part and bias part, link rate is very different. And also this one, layer 1 and layer 5 link rate also is very different. So the figure actually shows the dynamics of LARS, or the same thing to lab. So I just introduced the dynamic of LARS and lab. So why is it important? So let's go back to the small bay training first. We know small bay training actually can solve the sharp minimum problem. Why? Because they use the noisy gradients in the step computation. So actually the noise can push the optimizer out of the basin of the attraction of the sharp minimizer. And also the noise in light batch is not enough to cause optimizer get out of this basin. So we need a noise. But how can we add a proper noise to light batch training? So actually we tried the Gaussian noise. For example, we add a Gaussian noise to activation with gradients outputs. So a researcher before us, they also some researchers they did the same thing, but it didn't work. So the key thing here is how can we add a proper noise? So I think the dynamics of LARS and lab may be a proper noise. So right, so a dynamic can be a proper noise to help the optimizer get out of the attraction of the sharp minimizer. So and also the second thing is why LARS and lab can speed up training. So let me give you another figure, three-dimensional figure. The first dimension is trust ratio. Second dimension is iteration, and the third dimension is the frequency of trust ratio. So clearly you can see actually in the beginning, right? In the beginning, this can give you a natural per layer warm-up, right? Most of the trust ratio are tiny, so they can give you a natural per layer warm-up for all the layers. And also we can see across the training, some trust ratio are tiny. So this actually can make the stable layers to use a very aggressive or very light link rate without diverging. This is very important. So without a trust ratio, if some layers use aggressive link with other layer will diverge. So that's very important. So that's the reason why it can allow the optimizer to use aggressive link rate. And also the convergence rate, we can prove LARS and lab converge to a stationary point in a general non-convex setting. So we know that's the best thing people can do because the non-convex optimization is an NP hard problem. So also we can prove LARS and lab can converge faster than IGG in light batch training. So we know the conversion rate of IGG depends on the maxima of a smoothness across dimension or the maximum of the Lipschitz constants. However, the conversion rate of LARS and lab only depends on the average of the Lipschitz constants, which can be much faster. So let me also show you some exciting results of, for example, lab optimizer. So it's for BERT training on squad application. We increase base size from 500 to 32K, 64K. You see, we can reduce training time from 3 days to 76 minutes without losing accuracy. And also, so we also use LAMP optimizer for the ImageNet training. We can see it also works for ImageNet training. So the horizontal axis is a different optimizer, or vertical axis is validation accuracy. You see, so for LAMP, it can can even get a better accuracy than momentum IGG. So we think a LAMP optimizer is the first optimizer that work for both ImageNet training and NLP BERT training. For example, we know momentum IGD, it works very well for ImageNet training, but it failed for NLP like BERT. But on the other hand, so Adam they work very well for NLP like BERT, but they failed on image-generated training. But LAMB can work for both of them. So I also want to highlight the early success of LAMB of LARS optimizer. So in the last 3 years, researchers reduced the image-generated training time from 29 hours to around 1 minute. So the table shows the image-generated training speed of world records. So the world records were created by Facebook, Berkeley, Japan PFN company, Berkeley, Tencent, Sony, Google, Fujitsu, and Google again. So since 2017, all of them actually use LARS optimizer. You see, since 2017, all of them use the LARS. So also, we win the best paper award for our paper image-generated training in minutes at ICPP conference. So it's actually the most cited HPC conference in the last 3 years, and the techniques are being used at NVIDIA, Intel, Facebook, Google, and Tencent. And also LARS is being used in many different applications. For example, researchers can implement the LARS for their own applications. For example, here is a quote from deep learning researcher at Stanford. Also, LARS help the Jeff Hinton team to achieve state-of-the-art results on unsupervised learning. So if you want more, please check the paper by Jeff Hinton team, published at ICML 2020. And also LARS was added to ML Perf, which is industry benchmark for faster training. And we got many media coverage on LARS, for example, Science Daily, US National Science Foundation, and also communication of HCM, Intel, the next web. Also, I want to introduce the early success of LAMB. For example, LAMB helped the first AI to scale the transformer model to 120 GPUs. So here is a quote from first AI. You see, so LAMB is better than Adam, or even on a single machine. So if you want more, please check first AI blog post. Okay, so and also LAMB is being used by Microsoft Deep Speed system. So here you can see, here is a screenshot from Microsoft GitHub. You see, they actually use the LAMB. And also LAMB become optimizer for NVIDIA here. So here also a screenshot from NVIDIA public GitHub. So according to NVIDIA, LAMB is 17 times faster than Adam. So if you want to have a good LAMB implementation, please check NVIDIA public GitHub. So also LAMB help Google to achieve state-of-the-art results on Glue, Squad, and Risk benchmark. Also, it's being used by state-of-the-art NLP model like BERT. And even some second bias startups, they are now using LAMB optimizer. So they also use LAMB as interview questions, which means LAMB is widely used by different companies. And our early success have a final, we have a final summary here. So LAMB and LARS were mentioned by Google's official production release. So they help Google to train ImageNet or train BERT, train different deep learning applications very fast. So I just joined NUS. I'm building my group. So I'm looking for PhD students or master students and also research fellow and interns. If you want to work with me, I have many different projects. There are some exciting research directions like parallel deep learning, federated machine learning, second order numerical optimization, model parallelism, memory efficient optimization, hyperparameter optimization, communication efficient algorithm, efficient communication kernels, light scale deep learning, like GAN or reinforcement learning. So if you want to know more, you can actually check my homepage. For example, you can scan the QR code. You will get my email on my homepage. Thank you. Let me know.